In hydraulic systems, actuators convert the flow of pressurized liquid into mechanical energy and motion. This motion can be in a straight line or linear, like this cylinder. In a cylinder, a piston moves along the length of the cylinder body, pushing the piston rod against the load. One end of the cylinder has an inlet port for fluid to enter under pressure. The other end is vented. The motion can also be circular or rotary, like this motor. In a motor, the shaft is attached to a rotating group, which turns as pressurized fluid enters one side of the motor housing and exits the other side. The rotating group is positioned off-center in the motor housing. This offset exposes more area of the top vane to system pressure than the lower vane. As a result, the force on the vanes is unbalanced and the shaft turns. The basic operating principles of all actuators are the same, whether they operate with a linear motion or with a rotary motion. In this lesson, we'll examine these basic principles and see how they apply to the operation of all actuators. Let's begin with linear or straight line actuators. The most common type of linear actuator is the cylinder. We learned in an earlier lesson that when fluid pressure is applied to the piston face, it generates a mechanical force which moves the piston rod and the load in a straight line. How much pressure is required to generate the force needed to move a specific load can be calculated using Pascal's law, which states that the pressure is equal to the force divided by the area against which the pressure is applied. This is written as P equals F divided by A. Now there's an easy way to remember this formula. In this triangle, if we cover up what we are looking for, we can see the relationship with the other two. For example, if we are looking for pressure, we cover pressure and we see that it equals force divided by area. If we are looking for what area will transmit a certain force at a certain pressure, we cover area and see that we have to divide the force by pressure. If we are looking for force, then it's pressure times area. Remember that force is at the top of the triangle. In a cylinder, the area we apply the pressure to is the face of the piston. Frequently, though, we don't know the area of the piston face. Usually what we have is the piston's diameter, or the bore of the cylinder as it's called. That's the distance from side to side through the center of the bore. Finding the area is easy. As you can see by the illustration, the area of any circle is just slightly more than 3/4 the size of a square with sides the same length as the diameter of the circle. Actually, the circle encloses 0.7854 of the area of the square. To find the area of a square, we multiply the length of one side by the length of another. So, to find the area of a circle or a piston, we use the formula circle area equals diameter times 0.7854, or d squared times 0.7854. The 0.7854 in this formula is called a constant. For example, suppose we have a 6,284-pound load that has to be moved by a cylinder with a 2-inch bore. To calculate the pressure required, we divide 6,284 pounds by the area of the piston. That area is 2 inches times 2 inches times 0.7854, or 3.1416 square inches. 6,284 pounds divided by 3.1416 square inches equals 2,000 pounds per square inch. To move the load, the hydraulic system must operate at a pressure of 2,000 psi. In the real world, of course, we also have to account for friction and other inefficiencies in hydraulic systems. So to really move a load, we'd have to apply more pressure. How much more depends on the efficiency of the system. However, for the purposes of this lesson, all of the examples assume that the system is operating at 100% efficiency. In addition to pressure, force, and area, we may also have to know the speed at which a cylinder works. The speed of a cylinder is the velocity at which the piston rod moves. It's usually measured in inches per minute. The speed changes depending on how fast the cylinder fills up with fluid. If it fills up slowly, the rod moves slowly. If it fills up quickly, the rod moves quickly. How fast it fills up is called the flow rate, and it's often measured in gallons per minute. Sometimes the flow rate is given in cubic inches per minute. When this is the case, you can convert the flow rate to gallons per minute if you divide the GPM by 231, the number of cubic inches in a gallon. The speed at which the piston rod moves can be calculated by dividing the flow rate in cubic inches per minute by the area of the piston in square inches. We can use the same technique as before to help us remember this formula. For example, if we want the formula for speed, we cover speed, and we see that speed equals flow rate in cubic inches per minute divided by area in square inches. If we are looking for what size cylinder will be needed to achieve a specific speed at a particular flow rate, we cover area and find that we need to divide the flow rate by speed. Or if we want to know what flow rate will be required to produce a certain speed, then it's speed times area. Remember that the flow rate, expressed as cubic inches per minute, is at the top of the triangle. Suppose we need to determine the flow rate necessary to move a load 48 inches per minute using a cylinder with a 3-inch bore. To calculate the flow rate, we multiply 48 inches per minute times 7.07 square inches. That's the area of a piston with a 3-inch diameter. The answer is 339.36 cubic inches per minute. Let's look at another situation you might run into. Suppose you need to know how fast a piston will move if the bore of the cylinder is 3 inches and the flow rate is 1.5 gallons per minute. Using the triangle, we see that to determine speed, we must divide the flow rate by the area of the piston. If the flow rate is given as 1.5 gallons per minute, we need to convert that to cubic inches per minute by multiplying it by 231, the number of cubic inches in 1 gallon. So we have 1.5 times 231 cubic inches, which equals 346.5 cubic inches. The area of the piston is the same, 3 inches squared times 0.7854, or 7.07 square inches. The final step is to divide the flow rate in cubic inches per minute by the area in square inches. The answer, 49 inches per minute. Now, when it comes to rotary actuators, the formulas used to calculate speed and flow are very similar to the ones for linear actuators. Keep in mind, however, that in a rotary actuator, the movement is circular rather than linear, so speed is given in revolutions per minute rather than inches per minute. Our formula for calculating speed in a rotary actuator, like a motor, is flow rate divided by the volume or the displacement of the motor. The displacement is usually expressed in cubic inches per revolution. For example, to figure the speed of a motor with a 20 cubic inch displacement and a flow rate of 10 gallons per minute, we multiply the flow rate of 10 GPM times the constant 231, the number of cubic inches in 1 gallon, and divide that by the displacement of 20 cubic inches. Our speed is 115.5 revolutions per minute. Notice that we can also calculate the flow which a motor requires to maintain a certain speed if we know the displacement. For example, a 20 cubic inch motor operating at 115.5 RPM will require a flow of 2,310 cubic inches per minute. That's 10 GPM. Force in a rotary actuator is a little different than force in a linear actuator. In fact, the word force is not even used. Instead, we say torque, which means rotary force. How much torque is created depends on how far the force is applied from the shaft of the actuator. If a force of 50 pounds is applied 10 inches from a pivot point, 500 inch-pounds of torque will be generated. If the force remains 50 pounds but is applied 5 inches farther out from the pivot point at 15 inches, then 750 inch-pounds of torque will be generated at the pivot point. A rotary actuator, like a motor, generates torque in the same way. If the displacement of the motor in a system is increased, the torque it can generate from any given pressure will also increase. Larger motors will generate more torque at the same pressure. To calculate the torque of a rotary actuator, we multiply the pressure in pounds per square inch times the displacement of the actuator in cubic inches and divide by a constant 6.28. Now remember, all of our examples assume 100% efficiency. For example, if the pressure is 1,000 pounds per square inch and the displacement of the motor is 10 cubic inches, then the torque is 1,000 times 10 divided by 6.28, or a little more than 1,592 inch-pounds. The force triangle for linear actuators can be adapted for use with rotary actuators. Force becomes torque, and area becomes displacement divided by 6.28. Just as before, we cover up what we are looking for. For example, suppose we need to figure out how much pressure will be required to produce a specific torque. We begin by dividing the displacement by the constant 6.28. Then we divide the torque by that number. Or if we want to know the displacement of a motor required to produce a specific torque at a given pressure, we just divide the required torque by the pressure, then multiply that number by the constant 6.28. Let's look at some examples. Suppose we want to know how much pressure must be applied to a motor with a displacement of 12.56 cubic inches in order to produce 2,000 inch-pounds of torque. We divide 6.28 into 12.56 cubic inches and get 2 cubic inches. We then divide 2 cubic inches into 2,000 inch-pounds and get the answer, 1,000 pounds per square inch. Or if we want to know how much displacement a motor has to have to produce 2,000 inch-pounds of torque when the pressure is 1,000 pounds per square inch, we divide 1,000 psi into 2,000 inch-pounds to get 2 cubic inches. 2 cubic inches is equal to the displacement divided by 6.28. So the displacement of the motor must be 6.28 times 2 cubic inches, or 12.56 cubic inches. Now that we know how to determine the speed of actuators and the force or the torque they create, we can use that information to help us calculate how much power they can produce. We saw in an earlier lesson that work is done when force is applied and moves a load a distance. The distance through which force is applied determines how much work is done. In the case of a cylinder, the distance the load is moved is measured by the stroke of the piston, often in inches. Calculating the amount of work a cylinder actually performs is simply a matter of multiplying force times distance. For example, if a piston has a 12-inch stroke and we apply 500 pounds of force, we would say that the work done was 1 foot times 500 pounds, or 500 foot-pounds. Sometimes we need to be able to determine how much power is being generated in a hydraulic actuator. Remember from an earlier lesson that power is the amount of work done within a certain time, usually expressed as horsepower. 1 horsepower is equal to 550 foot-pounds of work per second. If an actuator moves 550 pounds 1 foot, we say it has done 550 foot-pounds of work. And if it does that work in 1 second, we say it has produced 1 horsepower. For example, suppose we need to know how much horsepower it will take for a cylinder to move an 11,000-pound load 12 inches in 10 seconds. Our formula says that horsepower is equal to speed times the force. The speed is 12 inches or 1 foot every 10 seconds, while the force is 11,000 pounds. 1 foot times 11,000 pounds is 11,000 foot-pounds, which must be divided by 10 seconds. That gives us 1,100 foot-pounds per second. Since 1 horsepower equals 550 foot-pounds per second, the cylinder must develop 2 horsepower in order to move the 11,000-pound load 12 inches in 10 seconds. If we want to know the speed at which an actuator will work, we cover up speed and see that we have to divide horsepower by force. If we want to know the force needed to achieve a certain speed, we divide horsepower by speed. When making your calculations, be sure you use the correct units. Otherwise, your answer will be incorrect. Now, sometimes we don't know the speed or the force. For example, suppose all we know is the pressure and the flow rate. We can use a different, simplified approach that uses a special constant to establish the relationship of horsepower, pressure, and flow rate. The simplified formula for horsepower of a linear actuator is the flow rate in gallons per minute times the pressure in pounds per square inch times the special constant, 0.000583. As an example, suppose a cylinder takes 12 gallons per minute at a pressure of 1,000 pounds per square inch. What horsepower will it develop? To find the horsepower, simply multiply 12 times 1,000 times 0.000583. The answer is 6.996, or about 7 horsepower. The simplified formula for horsepower in a rotary actuator is speed in revolutions per minute times torque in pound-inches divided by the special constant 63025. For example, how much horsepower will a motor operating at 220 revolutions per minute deliver if it develops 2,000 pound-inches of torque? To find the horsepower, we simply multiply 220 times 2,000 and divide by 63025. The answer is 6.9814, or again, about 7 horsepower. Notice that in order for the formulas to work correctly, you must make sure the proper units of measurement are used. For linear actuators, flow must be in gallons per minute, pressure in pounds per square inch. And for rotary actuators, speed must be in revolutions per minute, and the torque must be in pound-inches. This completes our lesson on hydraulic actuators. In the next lesson, we will look at how we control the energy in a hydraulic system.